Professor Joao Sousa is professor at the Electrical and Computer Engineer Department from Porto University in Portugal. He has his PhD and master in electrical engineer, both of which were awarded by the University of Porto. His research interests include autonomous underwater, surface and air vehicles, planning and execution control for networked vehicle systems, optimization and control, cyber physical systems, and application of networked vehicle systems to the ocean science, security, and defense. In the past 35 years, he has involved in several projects, several technical committees, and also that include the NATO committees and also Sweden Marine Robotics Center. So Professor Joao Sousa, you are welcome, and you can come in for your presentation.
Thank you very much. Good morning, buenos dias. First of all, I would like to say it's a pleasure and an honor to be here. I'm really happy with this kind invitation. And so now I'll talk about future operations with multi-domain maritime unmanned systems. And I'll discuss the systems of systems perspective. And so this is the outline of my presentation. So I'll start with an overview of what we do at Porto University, then an aside on complex systems and control architectures. Then I'll go into operations with multiple UXVs. And this will provide the background to discuss some recent trends and where are we going next. And this is the reason why we are here, the blue planet. This was alluded to before. But this is beautiful, but it's a bit misleading. And the naked reality is that there's not much water in the planet. So this sphere represents all of Earth's water, and as you can tell, it's not big. And the small one represents fresh water. So, and there's an important observation by Walter Munk in regards to oceanography, but the ocean is still undersampled for several reasons. And this is one of the reasons. So if you look at observation footprints for different assets or technologies, if you will, in X you have distance, and in Y you have time. And then if you look, for example, for AUVs, they have kind of a small footprint in terms of observation. Then if you look at floaters and drifters, a kind of different footprint. But the important observation is that if you really want to observe something in those scales, you can see this a kind of a sort of a circle here, distorted circle. It tells you that to do the right thing, you need multiple assets to achieve some decent observations. Now I'll switch to what we are doing in our lab at Porto University. So we've been designing, building, deploying autonomous underwater surface and their vehicles for networked operations. Applications include ocean sciences, security and defense. And we've also been developing the software that enables all of these systems to work together as a system. So, and this is our vision for a sustained presence in the ocean. Definitely you'll need multiple assets, but probably more important than these multiple assets are multiple interactions. So interoperated communication links, sensing links, mixed initiative interactions, meaning operators in or on the planning and control loops. Vehicles will come and go, same thing with the operators. There's also the issue of scalability. Now we know how to handle, let's say, 10, 15 vehicles at a time. What about 100? What about 1,000? We are not there yet. We've also been using vehicles as data mules when you don't have permanent connectivity. There's also the issue, even more and more, about distributed computations. Then using some terminology from computer science, you can talk about physical mobile locality, which basically means that you can talk about launch and recovery by other assets. But in our view, we want to treat this ensemble of assets as a system that has properties that are a function of the vehicles, a function of the communication networks, and a function of the interactions that you establish over these. So we want the system to have organization-like properties. So we want to issue high-level directives, commands, objectives, doesn't matter, such as go and find this, or sample this area, or find the source of this plume, and then it will be up to the vehicles to organize themselves to achieve that goal. Of course, you can say this is PowerPoint engineering, granted, but we are developing the tools and technologies to achieve this vision. So in our lab, we have lots of different assets and also lots of different units. We've been mainly designing, building, and deploying most of them. We have some exotic ones. For example, this one in the bottom left, it's an octocopter that can take off and land from water, and it's what we call a flying modem. We also have Autonaut. This was not built by us, but all the computer systems and electronics are ours, and this can cross the Atlantic. And the important thing is that most of these vehicles share the same software infrastructure and some of the computational infrastructure. Moreover, these are interoperable, meaning that they can talk to each other. So we have different types of assets. LAUVs, this is an old one. Then USVs, UAVs, and then again the flying modem. For the AUVs, you just need to make sure that there's water when you throw it in the water. It happened before that people were not that careful. Something that is very important for us is software, the software behind all of these vehicles. So that's what we call our software tool chain. So we have Dune running on board. You have IMC, which is our protocol for communications. So all of our assets and control stations talk IMC. Then you have Neptus for planning and execution control that runs on your laptop. And then you have recent Ripples. It's a more recent development, which basically exposes all of these on the internet. So, and then we have different assets powered by our software tool chain. And then we also have other support for other interoperability frameworks, for example, Cattle. And Cattle plus Ripples. Then we have a web-enabled control center. You can see it here in operation on a ship. So we also have onboard deliberation. So, for example, we have T-Rex running on our vehicles. And without going into details, what you can say that we have is, so T-Rex is running on our vehicles, then it receives high-level objectives. And then new plans are generated on board when new objectives are received or when there's an error executing some objective. But we went one step further, which is, in addition to have multiple assets running T-Rex, we also had another planner called Eroptus running on a ship that was generating coordinated objectives and that were sent to these guys for execution. Ripples, just a kind of a brief overview. So it's a multi-vehicle planning execution control, 24/7. So it has supports for multiple maps, interoperability standards, multi-domain communications. For example, from Ripples, we can basically talk with a submerged submarine. We also have user access control. We support hierarchical C2 architectures. We ingest data from multiple sources. We have configurable alerts, multiple visualization layers, and this gives you a flavor for some of these visualization layers from Ripples. And we have a spin-off, OceanScan. So they commercialized the light AUV. I think for the moment there are over 100 of those in operation all over the world. And recently we were funded to start the Center for Atlantic Operations, so we are going for Atlantic Operations. The model is basically the same, so multiple assets, long endurance, and we also want our partners to be able to access our infrastructure and run these operations. Of course, we are, let's say, our pool of assets is increasing. And these are some of our operation areas. So we still need to go to Antarctica. Next year, hopefully we will be there. And now an aside on control architectures. Why? Because this relates to this notion of systems of systems. So let's think about a completely different problem, which is, for example, how to maximize throughput in highways. So and the question is how to decompose a complex problem into manageable subproblems. And this was a while back when Praveen Varaya at UC Berkeley came up with this idea, okay, why don't we come up with platoons? And if a platoon is running at something like 60 miles per hour with spacing between cars in the order of 2 meters, then not only can pack more cars per kilometer, but if they all travel at the same speed, you also increase throughput. Now think about the whole highway and how do you go about that. And he came up with this hierarchical control architecture. This was a while back, but it's still quite relevant. So you have vehicle dynamics, so basically accelerator, brakes, whatever. Then you have regulation, which takes care of maneuvers, joint platoon, switch lanes, this and that. On top of that, you have a coordination layer, which takes care of motion coordination among several vehicles. And then you have the link layer. The highway has links between junctions. And then what is set here is the nominal speed for that link that all the platoons should follow. And then on top of that, you have a network layer that takes control of traffic distribution. And so you see here, a very complex problem was partitioned into manageable subproblems using different models. Different problem, and actually here we use exactly the same technologies. So mobile offshore base, without going into, this was a feasibility study. The idea was to align several modules under DP, and then being able to extend flexible bridges among them, or between them. So then again, a layered control architecture. Another one, which is a bit more crazy, mixed initiative control of automated teams, in which we were given a complex task, and then we were given threat models, and then we were supposed to go and remove some stuff from the map. And then again, we came up with a hierarchy of planning and execution control without going into details. So we started with primary targets, then you would select secondary targets, and then you had target sequencing and paths, tasks and subtasks, team allocations and deadlines, and then execution control. So this is to say that planning and execution control of large-scale systems is really important for what we want to do in the future. And there are several principles aimed at establishing a scientific framework for analysis and design. So the principle of self-containment, the principle of coherence, and other principles. Curiously, this is quite recent. There is this paper by John Doyle, one of the big names in controls. It came out recently towards the theory of control architecture. So I would like to revisit this soon. Now let's briefly talk about operation with multiple UXVs. By UXVs, I mean UUVs, USVs, and UAVs. So, and I'll talk about stuff that we did in the past, in which we had systems with evolving complexity, but no higher layer, higher level of organization abstractions. Let's be a bit more concrete about this. So we've been, I co-founded, and we've been co-organizing the REP-MUS exercise that you see here. So it's being jointly organized by us, by the Portuguese Navy, by NATO, CMRE, and also EDA. It's a large-scale exercise. It's about operational experimentation and about evaluation and testing in operational scenarios. And then this is developed in the triple helix framework. So you have academia, industry, and the armed forces all working together. And there are several focus areas. And these are some of the assets that we use in this exercise. This has been growing a lot. So, for example, into 2024, this took place in September. This is an annual exercise that started in 2010. We had 23 participating countries and several observer countries. And I don't have the exact figures for 2023 and 2024, but just to give you a sense for size, so in September, we had over 62 UUVs operating in Sesimbra, in Portugal, under this exercise. One of the focus areas is interconnectivity, which has to do with the interoperability, and also interchangeability, being able to hand over assets between control centers. We have a very complex, and this is also very important, we have a very complex task organization structure. This is basically the human side of it, quite complex, because keep in mind that we had lots of assets here. So not only manned assets, but also manned vessels. For example, we had 18 ships involved in this exercise. Now, this is our perspective about eye-to-eye interoperability into interchangeability. So this is our view from Porto University. So we have some of our assets, like the LAUVs and Manta gateways that can talk with Neptus, now going back to software, and can also send information directly using SATCOMs to ripples to the cloud, which basically also services a control center. And this control center also ingests data coming through different networks to ripples, and this data is broadcasted by all of the other assets. So basically, we can see what is going on in this region, and we can also retask vehicles. So this is really large scale. A few simple examples of what we've done over the years. This is just Porto University and some of our partners. For example, having a control station exchanging commands and data with a submerged UUV, using first a UAV, then a wave glider with a communications gateway. It worked pretty well. Then we've also been playing with manned submarines, and we did several different things. So we tested acoustic communications between Arpão, which is one of our submarines, and the LUV for situation awareness, but also for being able to task the LUV from Arpão. We also had diver-assisted launch and recovery of LUV from Arpão, and we also participated in this distress signal response exercise. Then again, now talking about some complex operations. So imagine that you have surface and UUVs, and you have onboard and offboard software, and you have mission specifications for a group of heterogeneous vehicles. You have systems-level planning and execution control with minimal human intervention, one operator, and then you have interfaces for heterogeneous vehicles. And this gives you a flavor for what was done there, a compressed flavor, of course. So multiple assets, and then this is the perspective from Neptus. So to the right, you can see these boxes that these allude to different vehicles. And then again, you can specify, hey, I want you guys to map this area. Then the area is split into several sub-areas, and then these guys are supposed to map these areas, and if there's a problem between them, they reach some agreement using acoustic communications to redistribute tasks. Another example, somewhat complex, about interoperability. So we had some of our AUVs underwater. There were some AUVs from the Undersea Warfare Center, Newport, Rhode Island. There was a seabed node with acoustic modems. There was a WAMV, a surface vessel, with a communications gateway, so enabling underwater and above water communications. Then we had our flying modem, and the operator could send commands and mission plans to the flying modem that then could land close to the seabed node and send data and commands to the seabed node. And same thing could be done with the help of the USV and the AUVs. But the thing is, once data or mission plans were available in the seabed node, then UUVs could go by the seabed node and extract mission plans. Something that we did this year, this was the first attempt in this direction, was counter UXVs. This year was just about the detection. So we had several USVs towing acoustic arrays. We also had vector acoustic sensors mounted on buoys. The idea was to be able to detect other UUVs operating in the area. And then this data was fed to a command center. In this command center, we had a sort of a synthetic model of what was going on there. And then based on that, we were able to retask the USVs to basically maximize probability of detection. Something else that we did, then again, quite relevant, was this cruise in the Pacific. I had a big team. This is part of my team. This took place on board the RV Falcor. So we had people from Spain, from Portugal, US, and Norway. We also had support from NASA, Ames, and SINTEF. And this was the main goal of the cruise, to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal resolution. So I have a short video here. There is some sound, but if there's no sound, okay, perfect, thank you.
During this expedition, our team has created a system to conduct oceanographic surveys with unprecedented levels of detail and scale. Approximately 1,000 miles off the coast of Southern California, we are studying the subtropical front. Here, two masses of water collide, which generate a unique mix of physical, chemical, and biological features. Before the expedition, autonomous vessels helped us determine the approximate location of the front. When we arrived here, we deployed CTDs to gain a more precise understanding of its spatial dynamics. Our autonomous underwater vehicles, which were specifically designed for this expedition, can cover hundreds of kilometers and stay in the water for up to 50 hours. They travel in a yo-yo pattern, sending real-time data back to the ship every time they surface. Our fixed-wing vertical takeoff UAVs can fly faster and further than quadcopters and carry a variety of sensors. The data our autonomous vehicles collect helps us locate biological hotspots where we conduct more detailed sampling.
We are deploying very advanced technology that needs to be refined through experimentation, and by doing that we hope to establish some of the foundations for the future of oceanographic survey. Okay, so we had a complex ocean observation system based on the Falcor. So we deployed 7 UUVs from the Falcor. We had the support of 1 wave glider and 2 sail drones, USVs. Then for communications, we were using SATCOMs, and then we're kind of handling all of this data with the help of ripples. So we had a control center on board the Falcor and another one in Portugal. This is exactly what you had. So we were operating 24/7 for about 2 weeks. And so different views. This was a view from the Falcor in the control center. And some 3D view of the front, which was very exciting. We saw some very interesting things.
So we take all these different systems that go beyond the footprint of what a ship can do. They can be 20 miles this way, 20 miles that way, and help us understand the oceans a lot better than we do now.
So the important thing here is that we had a huge operational footprint. So our op area was in the order of 40 nautical miles by 50 nautical miles, always having vehicles in the water to observe what was going on there. Next year, we'll run this experiment. So we'll have one of our USVs crossing, hopefully. You never know with the ocean, as you know probably much better than me. So we'll have one of our USVs crossing from continental Portugal to the Azores, and along the way, so there will be some deviations from the optimal path to maximize the scientific return. Now, I would like just to say a few words. Of course, this is not a thorough discussion of recent trends, but just a few words. The first one is this observation by Ray Kurzweil from 2001, which says that technological change is exponential, and returns such as chip speed and cost effectiveness also increase exponentially. And actually, if you look at some market trends, yeah, this kind of seems right, but there's a problem which is captured under what people call the Martek's law, which basically states that technology changes exponentially fast, but organizations change logarithmically slow, meaning that this gap increases with time. And so this eventually will require a reset of the organizations, and this reset can be quite radical. From our perspective, we need, and now looking back at what we did in the past, we need new abstractions, vehicle capabilities, composition, in some sense to be defined, teams, inter-team coordination, different organization structures, and we need to go back to the scientific method with operational experimentation. So develop your concepts, ideas, you test them, then you go about operational experimentation, and then you come back to the drawing board if there's a need to. Autonomy, yes. Lots of people are talking about autonomy. We are all in favor of autonomy. Our friends, for example, from Girona, we are all in favor of this, but still there's a, what about number of operators per vehicle? 0? Not necessarily. So this came out recently, for example, self-driving cars and so-called robo-taxis. And for example, one of the companies has, on average, 1.5 operators per vehicle. So we are not there yet, and in the RAP-MUS, we even had more operators per vehicle. Another idea, and so I was part of the Innovation Advisory Board to the MUS initiative from NATO. And we came up with this idea, the digital ocean, that was then again submitted by NATO, and it was approved by NATO, and they started this initiative this year. There was the first digital ocean conference, and this provides a kind of motivation for future developments.
NATO's vision of a digital ocean will be implemented through the creation of a vast, global-scale network of sensors, from seabed through the ocean's surface to space, across millions of miles. It includes unmanned surface vessels, subsea sensors, satellites, ships, buoys, and drones. It builds on the assets we already have and creates an interconnected mesh of immediate data and communication fused together with AI algorithms, computer vision, and acoustic analysis technologies powered by machine learning, all coming together to create a multinational advanced ocean management platform, the digital ocean. A digital ocean will help us mitigate the risks of climate change, protect undersea critical infrastructure, and safeguard essential supply chains and strategic waterways. It will help us counter piracy, illegal fishing, and trafficking. Because ultimately, we need to see our oceans to protect them. A digital ocean will help us do that more affordably, sustainably, and safely.
Okay, so this kind of presents a challenge for the future, and this is why I would like to discuss where are we going next, at least from our perspective, and I think it's not only from our perspective. First of all, we need to be a bit more ambitious in the sense of the type of systems that we are dealing with. So we want to have systems of systems endowed with dynamic layered organization structures, and keep in mind that for the moment people only talk about vehicles, but we need vehicles with different organization structures that incorporate teams, inter-team coordination, creation and deletion of teams, load balancing between teams and with operators on the loop and not in the loop. Then again, going back to our first comments, or one of our first comments, we want to have a system that has properties that are a function of the assets, a function of the communication networks, and a function of the interactions that you establish over these. Of course, it's difficult to make predictions, especially about the future, but we try. Now, kind of some observations. First of all, how to cope with scale and complexity. And as you can tell, I'm going towards control architectures. First of all, terminology is confusing and hence dangerous. And semantic overload is even worse. For example, people have been talking a lot about swarming. Nothing against swarming. We've also done that. But we need to go beyond that. And so, but then again, who am I to say that? So Marco Dorigo, so he came up with his paper, Reflections on the Future of Swarms. It came up in Science Robotics something like 2 years ago. While swarm robotics takes inspiration from self-organization systems, future robotic swarms should include hierarchical forms of control beyond self-organization to deal with the assignment of larger responsibilities, task allocation, creation of task-oriented teams, and coordination of specific activities. And then again, I think that you all agree that this is not a swarm. So we need more advanced concepts. And how shall we go about that? Let's first discuss vehicles. Vehicles have some, let's say, can be organized into platforms, payload, mechanical interfaces, communication, command and control, software, and computation. But the observation is that most COTS vehicles are not designed for interactions, period. Then you have some technical features, and then imagine that you buy a UUV from this vendor, a USV from another vendor, a UAV from some other vendor, and you also have some hybrid vehicle. But the important thing is that if these guys are not compatible up to a certain extent, in terms of communications, in terms of interoperability, in terms of cooperation skills, what can I do that can be of use to other guys? There's not much you can do with them as a team. You can operate those as single entities, but not as a team. On the other hand, if you look at this matrix of capabilities, and if these guys are somewhat compatible, then you can operate those in such a way that you can get out of a team, notion to be defined. You can get some team capabilities that were not there before. They were not there in each individual vehicles. And this is an important observation for teams. And now you can be a bit more ambitious, and this is pretty much my last slide. Then you can go into systems of systems, but being quite ambitious here. So you can have vehicles, then you can organize those into teams. Teams in turn can have sub-teams. Then you can also have control stations with operators, different control centers, handover of command and control between these centers. And then, for example, some teams can have different properties. Team A is not allowed, this is what this continuous red line represents, is not allowed to interact with other assets outside. Same thing with TB, but these are allowed to exchange assets between them. Now, if you look at Team C, here there's a team lead, then you have different sub-teams, and each of these teams or each of these sub-teams have different control strategies. Some of them could be leader follower, and others could be, for example, pretty much decentralized. If you go for a leader follower, you can use, then again, you can go into game theory, and there are some recent developments in game theory and machine learning, which seem quite interesting. And the interesting abstraction here are Stackelberg games. But then again, Team C is allowed to interact with other external assets. Of course, this is, I'm almost there. This is quite complex. We are working on this. As you can get, now we have the motivation to get here. We have the tools and technologies that will enable to get here. But still, we need more developments. So our research is at the intersection of control and computation. We need lots of different concepts from computation. So we have different types of mobilities, physical and computational, and even in computational mobility, there are different types. I won't go into details. Software and hardware, you need dynamic reconfiguration, you need dynamic access control, you need task composition and decomposition, we need hierarchical level fault identification and recovery, and then you need also new notions of behavior equivalence and satisfaction. And this is pretty much what I had to say, so thank you very much.
Thank you so much, Professor Joao. Questions? I have a lot of questions, but I prefer that people here. No questions? Okay, go ahead, please. I don't know. Maybe yes, you should. Yes. The mic is coming. Here.
Hi, Joe. Thank you very much for this very nice presentation. In this hierarchy that you were presenting on assets and sub-teams and teams and all this hierarchy, how do you imagine the communication with the human at the end, with all these resources that are available? And I think one of the challenging things also will be to how to transmit or have a dashboard in which the human is able to tell all this infrastructure what is the aim of what type of questions he wants to find out or discover or measure in the ocean.
Thank you very much. This is a great question, and this is also one of the reasons why we need hierarchies to basically kind of put limits on what we need to exchange to achieve some level of coordination. And for example, in this kind of a micro project, which was about suppression of enemy air defenses, was a bad application, but still very interesting from mathematical point of view. We realized that after a while, if you do it right in terms of organization, and to understand what is going on, you just need to monitor a few variables at each layer. So just by looking at a few variables at each layer, you can understand, hey, the state of the system is this right now, and because this is happening or so, probably the next state will be this one. And then you go up in the hierarchy. So first of all, you had the notion of, okay, how is the sub-team doing? How is the team doing? How is, then again, how are teams doing in terms of executing the mission that was assigned to them. And this is quite relevant to us, as you know much better than me, which is you also need to exchange data. And acoustic communications is not exactly the best way to exchange data. So this should also be incorporated in the control the architecture design so that you make sure that, hey, if you need high bandwidth, then you should have assets that could take care of that to basically make sure that you get some data every now and then, let's say through some high bandwidth kind of means of communication. So, but it's still a very tough question. So, as you know, I'm looking forward to your presentation by, let's say, getting lots of data from, let's say, video or so. Yeah.
Thank you.
Thank you.
Another question? I have one for you. It's related to the awareness of the underwater system. How do you, in terms of cooperative multi-agent system, I realize that your underwater robots are homogeneous, or I mean that all of them have the same capabilities, or?
No.
No?
Not exactly.
Not exactly?
Yeah.
And they know what happened to their partners? I mean, what is the level of awareness that you have in the underwater environment?
Okay, yeah, which is a related question. So then again, it boils down to communications, but also something else, which is cooperation skills. So in some of these experiments, so when a vehicle joins a network, it announces. Then again, the meaning of announcement is, there's a question mark here, but let's kind of take this abstraction. Announces its capabilities, so that the other guys in control centers know their capabilities, so that when start interacting, they know, hey, this guy has a very nice side-scan sonar or a nice video camera. This guy is quite poor in terms of navigation skills, but if there's another vehicle that is quite good in terms of navigation, then probably this guy can help the other one in terms of navigation. So the first step is broadcasting or announcing their capabilities. And second one is making sure that you receive those so that you can take decisions. Of course, by receiving those, it doesn't mean that you receive those in real time. There could be some delays, and this should also be accounted for in the control architecture.
Thank you so much.
Thank you.
We are going with the next speaker, so thank you so much, Professor Joao, for your talk.
Thank you.